Before we dive into one of the most incredible stories of World War II, a story of rebellion, genius, and pure audacity, I need you to do something for me. Hit that like button right now, smash that subscribe button, and drop a comment telling me where you're watching from. Are you in the States? The UK? Maybe somewhere in Asia or Europe? I want to know. It's 1943. You're a P-38 Lightning pilot stationed in the sweltering heat of New Guinea. Your fighter, one of the most advanced aircraft in the world, should be dominating the skies. But instead, you're getting outmaneuvered by Japanese Zeros. Your engines are choking. Your performance is gutted. And headquarters is telling you there's nothing they can do about it. Then one day, a mechanic approaches you with a wild idea. What if, he says, we just remove this? He's pointing at a critical engine component. You think he's crazy, but you're desperate enough to let him try. This story matters because it reveals a fundamental truth about innovation. Sometimes the biggest breakthroughs don't come from the top down. They come from the bottom up, from the people closest to the problem, the ones who see it every single day and refuse to accept that's just how it is, as an answer. In 1943, the Pacific War was at a critical juncture. American forces were island-hopping toward Japan, but air superiority was far from guaranteed. The Lockheed P-38 Lightning, a twin-engine, twin-boom fighter that looked like something out of science fiction, was supposed to be America's ace in the hole. It was fast, heavily armed, and could climb like nothing the Japanese had. But there was a problem. A big problem. When P-38s were deployed to the tropics, the scorching, humid environment of the South Pacific, they became shadows of themselves. Engines overheated. Performance dropped. Pilots were dying because their planes couldn't keep up with the enemy. Official channels were slow. Lockheed was working on fixes, but bureaucracy and engineering conservatism meant solutions were months or even years away. Meanwhile, every day, pilots were climbing into cockpits knowing their aircraft were compromised. That's when Charles McDonald, and mechanics like him, decided to take matters into their own hands. What they did was unauthorized, unsanctioned, and technically against regulations. But it worked. And in doing so, they proved that sometimes survival demands you break the rules. Let's set the scene. It's early 1943, and the Pacific Theater is a hellscape of jungle warfare, brutal heat, and desperate fighting. After the shock of Pearl Harbor and the fall of the Philippines, American forces have finally stopped retreating. Now, they're pushing back, island by island, mile by mile. But this isn't the war in Europe. There are no massive tank battles across open plains, no strategic bombing of industrial cities. This is a war fought across thousands of miles of ocean, where the only thing between you and the enemy is 25,000 feet of air. Air superiority isn't just important, it's everything. Enter the Lockheed P-38 Lightning. Designed in the late 1930s, the P-38 was unlike anything else in the sky. With its distinctive twin-boom design, tricycle landing gear, and twin Allison V-1710 engines, it looked more like a spaceship than a fighter plane. It could reach speeds of over 400 miles per hour, climb to 40,000 feet, and carry enough firepower to shred enemy bombers. The P-38 had already proven itself in Europe and North Africa. It was the aircraft that shot down Admiral Yamamoto's plane in 1943, killing Japan's most brilliant military strategist. Pilots loved it. Commanders trusted it. On paper, it should have dominated the Pacific. But paper doesn't account for reality. And the reality of the Pacific Theater was brutal. The P-38's Allison engines were designed for temperate climates, the kind of conditions you'd find over France or Germany. They had intercoolers to manage engine temperature, systems to regulate airflow, and components carefully calibrated for optimal performance in moderate heat. But the South Pacific wasn't moderate. It was a furnace. Ground temperatures routinely exceeded 100 degrees Fahrenheit. Humidity was suffocating. And when you're sitting on a runway in New Guinea or Guadalcanal, waiting for clearance to take off, your engines are already cooking. The P-38's intercooler system, designed to cool the compressed air from the turbochargers before it entered the engine, became a liability. In tropical heat, the intercoolers couldn't keep up. The air entering the engines was too hot. This caused detonation, premature ignition of the fuel-air mixture, which reduced power, damaged engine components, and sometimes caused catastrophic failure. Pilots reported sluggish acceleration, reduced top speed, and engines that ran dangerously hot. Some P-38s could barely reach 350 miles per hour, a far cry from their rated 414 miles per hour. Japanese Zero fighters, though less heavily armed and armored, were nimble and could exploit the P-38's degraded performance. This wasn't just an inconvenience. It was deadly. Pilots were being shot down not because they lacked skill or courage, but because their aircraft couldn't perform. Imagine being a 22-year-old kid from Iowa, strapped into the cockpit of what's supposed to be a technological marvel, only to realize you're flying a compromised machine into combat. Letters home told the story. One pilot wrote, "The Lightning is a beautiful plane, but out here, she's sick. We push her as hard as we can, but she just won't give us what we need." Headquarters knew there was a problem. Lockheed knew there was a problem. Engineers were working on solutions, revised intercooler designs, modified engine settings, improved cooling ducts. But engineering takes time. Testing takes time. Manufacturing takes time. And time was something the men flying these missions didn't have. So, out in the forward airfields, places with names like Dobadura, Port Moresby, and Nadzab, the mechanics started experimenting. To understand the desperation of the situation, you need to understand just how bad things had gotten by mid-1943. The P-38's engine troubles weren't just about speed. They were about survival. Each P-38 Lightning was powered by two Allison V1710 engines, each producing around 1,425 horsepower at peak performance. These were liquid-cooled, turbocharged engines, marvels of engineering. But they were also temperamental. The turbochargers compressed incoming air to maintain power at high altitude. This compression generated heat, a lot of heat. The intercoolers were supposed to cool that air before it entered the cylinders. In temperate climates, this system worked beautifully. But in the tropics, the intercoolers became overwhelmed. The ambient air used to cool the compressed air was already scorching hot. The intercooler radiators, essentially heat exchangers mounted in the leading edges of the wings, couldn't dissipate heat fast enough. Here's what happened as a result. 1. Detonation and pre-ignition. When hot, compressed air entered the cylinders, it increased the risk of detonation, an uncontrolled explosion of the fuel-air mixture instead of a smooth, controlled burn. Detonation hammers the pistons, damages cylinder heads, and can destroy an engine in minutes. Pilots heard it as a sharp knocking sound, like someone hitting the engine with a hammer. 2. Reduced power output. Hot air is less dense than cool air. Less dense air means less oxygen per cylinder. Less oxygen means less power. P-38s in the Pacific were losing 15 to 20% of their rated horsepower just from heat alone. 3. Overheating. Engines running too hot experienced oil breakdown, coolant boiling, and component expansion beyond design tolerances. Bearings seized. Gaskets failed. Pilots reported cylinder head temperatures spiking into the red zone, temperatures that, if sustained, meant engine failure. 4. Throttle restrictions. To prevent catastrophic damage, pilots were often ordered to operate at reduced throttle settings. This meant they couldn't use full military power or war emergency power, WEP, when they needed it most, during dogfights or emergency climbs. One pilot, Lieutenant Colonel Thomas J. Lynch, wrote in his logbook, "You can feel the plane struggling. You push the throttle forward, and instead of that surge of power you're used to, you get nothing. It's like flying with one hand tied behind your back." The statistics were grim. Between February and June 1943, the 5th Air Force in the Pacific reported that nearly 40% of P-38 mission aborts were due to engine problems. That's 4 out of every 10 missions scrubbed, not because of enemy action, not because of pilot error, but because the planes couldn't handle the heat. And then there were the losses. Pilots forced to fly at reduced speeds became easy targets. Japanese Zeros, though outgunned, were agile and could exploit any weakness. Records show that P-38 loss rates in the Pacific during this period were significantly higher than in other theaters. One particularly tragic incident involved a 4-plane patrol over the Bismarck Sea. All 4 P-38s experienced engine trouble within minutes of each other. 2 pilots managed emergency landings on Allied airstrips. 1 bailed out over the jungle and was never found. The 4th crashed into the sea. The psychological toll was immense. These weren't green recruits. These were experienced pilots, men who had trained for years, who trusted their machines. But now, that trust was eroding. Captain Richard Bong, America's top ace with 40 confirmed kills, many in AP-38, later said, "There were days when I wondered if I'd make it back. Not because of the zeros, I could handle them, but because I didn't know if my engines would hold together." Maintenance crews worked around the clock trying to keep the P-38s airworthy. They adjusted mixture settings, tweaked timing, replaced spark plugs, cleaned intercooler cores, anything to squeeze out a little more performance. But they were treating symptoms, not the disease. Officially, the solution was supposed to come from Lockheed and the Army Air Force's technical divisions. Engineers were redesigning the intercooler system, developing improved core designs with better heat dissipation. But these modifications required new parts, new manufacturing processes, and extensive testing. The timeline? Optimistically, 6 months. Realistically, a year or more. But out on those forward airfields, surrounded by jungle and enemy territory, the mechanics weren't willing to wait. They started asking a dangerous question. What if the intercoolers were the problem? What if, instead of trying to make them work better, we just removed them? It was heresy. It was reckless. And it was exactly the kind of thinking that would save lives. His name was Charles McDonald, though he might have been just one of many mechanics who independently hit upon the same idea. Records from the Pacific Theater are incomplete, and multiple units claimed credit for the modification. But the principle was universal, and the courage required was the same. McDonald was a staff sergeant, an engine mechanic with the 475th Fighter Group stationed at WWII, New Guinea. He wasn't an engineer. He didn't have a degree from MIT. What he had was experience, intuition, and a refusal to accept the status quo. He'd spent weeks watching pilots return from missions, their faces drawn with frustration. He'd seen the engine temperature gauges buried in the red. He'd pulled cylinder heads and found evidence of detonation damage, pitted pistons, cracked valve seats, carbon buildup that shouldn't have been there. And he'd read the technical manuals. He understood the theory. Intercoolers cool the compressed air, increasing density and preventing detonation. Removing them would mean hotter intake air, less power, and higher risk of engine damage. But theory wasn't matching reality. The intercoolers weren't cooling the air adequately anyway, not in this heat. And the extra plumbing, ducting, and radiators added weight, complexity, and drag. So McDonald started running numbers in his head. What if we bypassed the intercoolers entirely? What if we routed the compressed air from the turbochargers straight into the engine? Yes, the air would be hotter. Yes, there'd be some risk of detonation. But the engines were already detonating. And if they could eliminate the intercooler drag and weight, maybe, just maybe, they could recover enough performance to make it worthwhile. He approached his commanding officer with the idea. The response was predictable. Absolutely not. That system is there for a reason. Lockheed designed it that way. We follow the tech orders. But McDonald didn't give up. He talked to pilots. He talked to other mechanics. And he found allies, men who were just as frustrated, just as desperate for a solution. One night, working by flashlight in a revetment, McDonald and a small crew began the modification on a single P-38. They were violating direct orders, risking court-martial, and possibly destroying a $100,000 aircraft. But they did it anyway. Here's what they did. They disconnected the ducting that routed compressed air through the intercooler radiators. Instead, they ran new ducting that sent the hot, compressed air directly from the turbocharger into the intake manifold. Hotter air meant a leaner fuel-air mixture, which increased detonation risk. To compensate, they richened the mixture slightly, more fuel to cool the combustion process. This meant slightly higher fuel consumption, but it reduced the knock. The intercooler radiators, ducting, and associated plumbing weighed around 200 pounds per aircraft. They removed it all. Less weight meant better acceleration and climb rate. They retarded the ignition timing slightly to reduce the likelihood of pre-ignition. This cost a bit of peak power but made the engine more tolerant of hot intake air. The work took most of the night. When dawn broke, they had a modified P-38 sitting on the flight line, a plane that, by all official standards, should never have been allowed to fly. But they had a volunteer pilot. Lieutenant Jim "Red" Watkins had flown dozens of missions and was familiar with every quirk of the Lightning. He trusted McDonald. And he was willing to take the risk. The test flight was scheduled for early morning, when the air was coolest. McDonald and his crew watched as Watkins taxied to the runway, ran up the engines, and released the brakes. The takeoff was normal. The climb-out was normal. And then Watkins radioed back, "Holy hell! She's flying like a bat out of hell." He put the aircraft through a series of maneuvers, climbs, dives, hard turns. He pushed the throttles to military power, then to war emergency power. The engines held. The temperatures stayed manageable. And the speed was incredible. When Watkins landed and climbed out of the cockpit, he was grinning. "I don't know what you did," he said, "but this thing just gained 40 miles per hour. Maybe more." McDonald's modification had worked. By eliminating the intercooler drag and weight, and by accepting slightly hotter intake air, they'd unlocked performance that had been buried under layers of over-engineering. But there was a problem. The modification was still unauthorized. If higher command found out, there would be hell to pay. Word spread fast. Other pilots heard about Watkins' flight and wanted the same modification. Other mechanics, emboldened by McDonald's success, started performing the same bypass on their aircraft. Within weeks, dozens of P-38s in the 5th Air Force had been modified. And the results were undeniable. Mission reports showed improved speeds, better climb rates, and fewer engine-related aborts. Pilots were engaging the enemy with confidence again. But officially, none of this was happening. The modifications were done quietly, often at night, with no paperwork, no approval, no records. Then, inevitably, someone higher up the chain noticed. A senior engineering officer arrived at WWII to investigate reports of unauthorized field modifications. He was furious. He demanded that all modified aircraft be grounded immediately and returned to standard configuration. But the pilots pushed back. They went to their squadron commanders, their group commanders, anyone who would listen. They showed the performance data. They explained how the modification had saved lives. One pilot, a captain named Thomas Lynch, who would later become a double ace, confronted the engineering officer directly. "With all due respect, sir, you're not the one flying these missions. We are. And this modification works. Court-martial me if you want, but don't take this away from us." It was a standoff. On one side, official regulations and engineering orthodoxy. On the other, combat effectiveness and pilot survival. The resolution came from an unexpected source. General George Kenny, commander of the 5th Air Force, heard about the controversy. Kenny was a pragmatist, a leader who valued results over regulations. He flew out to one of the forward bases, inspected a modified P-38, and took it for a test flight himself. When he landed, his assessment was simple: if it works, it works. Make it standard. With Kenny's blessing, the modification was formalized. Technical orders were rewritten. What had been an illegal field fix became official policy, not just for the 5th Air Force, but eventually for P-38 units across the Pacific. Lockheed engineers, when they finally examined the field modification, were initially skeptical. But after testing, they had to admit, in tropical conditions, the simplified system actually worked better than the original design. A later Lockheed report grudgingly noted, "Field modifications to eliminate intercooler systems in tropical environments have demonstrated improved performance metrics." While not optimal for all operating conditions, these modifications are considered acceptable for Pacific theater operations. In other words, the mechanics had been right all along. The impact of McDonald's modification, and the dozens of other mechanics who independently arrived at the same solution, was immediate and profound. Operational performance. P-38s that had been struggling to reach 350 miles per hour were now hitting 390 to 400 miles per hour in level flight. Climb rates improved by nearly 15%. Acceleration in combat situations was noticeably better. Pilots reported that the aircraft felt lighter and more responsive. One pilot, Lieutenant Colonel Gerald R. Johnson, wrote, "It's like someone gave my Lightning a shot of adrenaline. She climbs faster, turns tighter, and when I need speed, she delivers." The 40 miles per hour speed increase wasn't just a number, it was a tactical advantage that changed the calculus of every engagement. Japanese Zero fighters, which had previously been able to escape diving P-38s by running at low altitude, now found themselves caught. P-38s could pursue and overtake them. Mission success rates. Between July and December 1943, after the modifications became widespread, the 5th Air Force reported a 60% reduction in mission aborts due to engine trouble. Aircraft availability improved dramatically. More planes in the air meant more effective bomber escort, more aggressive fighter sweeps, and better close air support for ground forces. Pilot confidence. Perhaps the most significant impact was psychological. Pilots who had been flying with one eye on the engine temperature gauge could now focus entirely on the mission. Trust in the aircraft was restored. Captain Richard Bong, who flew modified P-38s throughout his combat career, later said, "After the fix, I never worried about the engines again. I knew my Lightning would get me home." This confidence translated into more aggressive tactics. P-38 squadrons began engaging in prolonged dogfights, something they'd previously avoided. They escorted bombers deeper into enemy territory. They took on targets that had been considered too risky. Combat effectiveness. The numbers tell the story. In the 6 months following the widespread adoption of the modification, P-38 kill-to-loss ratios in the Pacific improved significantly. The 475th Fighter Group, the unit where McDonald served, became one of the top-scoring fighter groups in the theater, with over 550 confirmed aerial victories by war's end. The P-38 was back. It was no longer the compromised, heat-addled disappointment that had frustrated pilots in early 1943. It was a weapon, fast, deadly, and reliable. Enemy reaction. Japanese pilots noticed the change. Intelligence reports captured after the war included interrogations of Japanese airmen who specifically mentioned that P-38s became much faster in late 1943. One captured Japanese pilot stated, "We used to be able to escape the twin-tailed fighters by running at low altitude. But suddenly, they could catch us. We had to change our tactics." The modification didn't just improve American performance, it degraded Japanese effectiveness. Tactics that had worked for months were suddenly obsolete. Recognition and consequences. McDonald and the other mechanics who'd pioneered the modification were never court-martialed. In fact, many received commendations. McDonald was eventually awarded the Bronze Star, not for the modification itself, which remained somewhat embarrassing for official channels, but for exceptional technical skill and initiative in aircraft maintenance under combat conditions. It was a bureaucratic way of saying, "You broke the rules, but you were right." General Kenny later wrote in his memoirs, "Some of the best engineering in this war didn't come from the design boards in California. It came from grease monkeys in the jungle who refused to accept that something couldn't be done." Broader adoption. Word of the modification spread beyond the 5th Air Force. P-38 units in other Pacific commands began adopting it. Even some units in the Mediterranean theater, which operated in hot North African conditions, requested permission to implement similar modifications. By 1944, Lockheed had incorporated some of the field modification lessons into production aircraft. New P-38 variants featured revised intercooler systems that were more effective in high-temperature environments. But for the aircraft already in the field, the simple bypass modification remained standard. Production and logistics. The modification also had logistical benefits. By eliminating the intercooler radiators and ducting, maintenance became simpler. Fewer components meant fewer failure points. Replacement parts were easier to stock. Turnaround time for damaged aircraft decreased. One maintenance report noted, intercooler-related failures, which previously accounted for approximately 18% of engine maintenance actions, have been virtually eliminated. Lives saved. It's impossible to calculate exactly how many lives were saved by the modification. But consider this, if the modification improved aircraft availability by 60%, and if it prevented even a fraction of the engine-related emergencies that had plagued early P-38 operations, then dozens, perhaps hundreds, of pilots came home who might otherwise have been lost. Every pilot who didn't have to bail out over enemy territory, Every pilot who didn't crash on takeoff due to engine failure, every pilot who had just enough speed to escape a pursuing Zero, they all owed their survival, in part, to a mechanic who decided that the rules were less important than results. The human element. But beyond the statistics and the tactical improvements, there's a human story here. It's the story of mechanics like Charles McDonald who understood that their job wasn't just to follow tech orders, it was to keep pilots alive. It's the story of pilots like Jim Watkins who trusted a mechanic enough to risk their life testing an unauthorized modification. And it's the story of leaders like George Kenny who had the wisdom to recognize that innovation doesn't always come from the top. One mechanic, interviewed years after the war, summed it up perfectly. We didn't think we were changing history. We were just trying to fix a problem. The brass could have their regulations and their engineering degrees. We had wrenches, and we had pilots counting on us. That was enough. The story of the P-38 intercooler modification is more than just a technical footnote in aviation history. It's a masterclass in innovation, leadership, and the courage to challenge orthodoxy when lives are on the line. The engineers at Lockheed were brilliant. They designed one of the most advanced fighters of World War II. But they were thousands of miles away from the problem. They had test data from California, not operational experience from New Guinea. Charles McDonald and his fellow mechanics lived with the problem every day. They saw the consequences firsthand. They heard the frustration in pilots' voices. And because they were so close to the problem, they were able to see a solution that the distant engineers missed. This is a lesson that applies far beyond aviation. In business, in technology, in any complex endeavor, the people closest to the work often have the best insights. But organizations don't always listen to them. Hierarchies, bureaucracies, and credentialism can create barriers between problems and solutions. The P-38 story reminds us that expertise isn't just about degrees and titles. It's about experience, observation, and the willingness to question assumptions. McDonald's modification was unauthorized. It violated technical orders. By every official measure, it shouldn't have happened. But here's the thing, the rules were wrong. Or, more precisely, the rules were designed for a different context and hadn't adapted to the reality of Pacific operations. This doesn't mean rules don't matter. Rules exist for good reasons: safety, standardization, accountability. But rules aren't sacred. When following the rules produces worse outcomes than breaking them, you have a moral obligation to reconsider. The key is judgment. McDonald didn't break the rules recklessly. He understood the risks. He tested carefully. He had a pilot who trusted him. And when the modification proved successful, he advocated for it to be formalized. That's the difference between reckless rule-breaking and principled civil disobedience. McDonald wasn't trying to undermine authority. He was trying to solve a problem that authority had failed to solve. General George Kenny could have shut down the field modifications. He had every regulatory and bureaucratic reason to do so. But instead, he listened. He tested. And he had the courage to endorse something that came from the bottom up rather than the top down. Great leaders understand that their job isn't to have all the answers. It's to create an environment where the right answers can emerge and be implemented, even if those answers challenge conventional thinking. Kenny's willingness to override the engineering establishment and trust his pilots and mechanics changed the course of the air war in the Pacific. It's a reminder that leadership isn't about protecting your ego or defending established processes. It's about achieving the mission. The intercooler system on the P-38 was a marvel of engineering, in the right environment. But in the tropics, it was a liability. The solution was to remove it. This is a pattern that appears repeatedly in engineering and design. Complexity is often added with the best intentions, but it creates fragility. Simple systems are more robust, easier to maintain, and less prone to unexpected failure. The intercooler modification wasn't about adding something clever, it was about taking something away. It was about recognizing that more isn't always better, and that optimization for one set of conditions can be suboptimal for another. Modern engineers would call this context-dependent design. McDonald and his fellow mechanics didn't have that terminology. They just knew that what worked in Burbank, California, didn't work in the jungles of New Guinea. For the modification to succeed, multiple layers of trust had to exist. Pilots had to trust mechanics to work on their aircraft their lives depended on. Mechanics had to trust pilots to test modifications and provide honest feedback. Junior officers had to trust senior officers to listen. And senior officers had to trust that the people under their command knew what they were doing. Without that trust, the modification never would have happened. McDonald would have kept his head down. Watkins wouldn't have volunteered for the test flight. Kenny wouldn't have overridden the engineers. Trust is fragile. It's built over time through competence, honesty, and shared hardship. But when it exists, it enables extraordinary things. The P-38 intercooler story became part of Air Force lore. It's taught in maintenance officer courses as an example of field innovation. It's cited in engineering ethics classes as a case study in challenging authority. But its influence extends beyond military aviation. The story has been referenced in discussions of organizational innovation, creative problem-solving, and the relationship between experts and practitioners. Companies like Toyota have studied the story as part of their Kaizen philosophy, the idea that continuous improvement should come from all levels of an organization, not just management. Silicon Valley startups have used it to argue for move fast and break things cultures, though that's arguably a misreading. McDonald didn't break things recklessly. He fixed something that was already broken. Today, we face problems that seem insurmountable. Climate change, pandemic response, cybersecurity, infrastructure decay. These are complex, multifaceted challenges that require expertise, resources, and coordination. But the P-38 story reminds us that solutions can come from unexpected places. The teenager tinkering in their garage. The nurse who sees a better way to deliver care. The teacher who redesigns a curriculum. The software developer who automates a tedious process. We need to create systems that listen to these voices. We need leaders willing to say, "I don't know, but let's try your idea." We need to balance safety and standardization with the flexibility to innovate. And we need to remember that expertise comes in many forms. The person with the most degrees isn't always the person with the best solution. Charles McDonald survived the war. He returned to civilian life, worked as an aircraft mechanic for a few more years, then transitioned to a career in industrial engineering. He rarely spoke about the modification, and most of his neighbors never knew that he'd played a role in one of aviation's great field innovations. He passed away in 1987, largely unknown outside a small circle of aviation historians and retired pilots. But his legacy lives on every time someone challenges the status quo, every time a mechanic suggests a better way, every time a leader has the courage to listen to the people doing the work. If this story inspired you, hit that like button, subscribe to the channel, and drop a comment with your thoughts. Have you ever broken the rules for the right reasons? Have you ever seen someone challenge the system and win? I want to hear your stories. And if you want more stories like this, stories of courage, innovation, and the people who changed history from the ground up, check out the playlist on your screen. Thanks for watching. Until next time, keep questioning, keep innovating, and keep pushing forward.